Download this code from codegive.com, link in the description below. Memory usage in Prolog programs, a deep dive. Prolog, being a declarative language, abstracts away many low-level details of memory management that imperative languages like C or Java expose. However, understanding how Prolog uses memory is crucial for writing efficient and scalable programs. Inefficient Prolog code can easily lead to excessive memory consumption and poor performance. This tutorial will explore different aspects of memory management in Prolog, providing code examples and practical tips to help you write memory-conscious Prolog programs. 1. Prolog's memory architecture ***. Prolog systems typically manage memory in distinct areas, each serving a specific purpose. Code area, program space stores the compiled Prolog rules and facts. This area is usually static and read-only after the program is loaded. Stack, local stack/environment stack. The stack is used to store the environments of active predicates, goals, during execution. An environment contains local variables, variables specific to a particular predicate's instantiation. Choice points, information needed for backtracking. When a predicate has multiple clauses that might unify with the current goal, a choice point is created. This choice point holds the state of the computation, variable bindings, etc., so that the system can revert to this point if the first clause fails to lead to a solution. Control information, pointers to the calling environment, return addresses, and other control-related data. Heap, global stack. The heap is used for storing complex data structures, particularly compound terms, structures like point, x, y, list, 1, 2, 3, etc., and atoms that are not immediately part of the program code. This is where dynamic data resides. It's also used for storing variable bindings that need to persist across multiple stack frames, example bindings created at the top level and passed down into recursive calls. Trail. The trail is a stack-like structure that records variable bindings that need to be undone upon backtracking. When a variable is bound, assigned a value, within the scope of a choice point, that binding is recorded on the trail. If backtracking occurs and the system returns to the choice point, the bindings recorded on the trail are undone, effectively restoring the state of the program before the binding occurred. This mechanism is essential for Prolog's declarative semantics. Atom table. A table that stores all atoms, symbols, used in the Prolog program. Atoms are represented by pointers to this table, which ensures that atoms are only stored once, improving memory efficiency. 2. Memory allocation and deallocation ***. Stack allocation Stack allocation is very efficient and occurs implicitly when a predicate is called. A new environment is pushed onto the stack. When a predicate succeeds or fails deterministically, without leaving choice points, its environment is popped from the stack. Backtracking also causes environments to be popped, restoring the previous state. Heap allocation Heap allocation occurs when compound terms are created. Prolog automatically allocates memory on the heap to store the structure and its arguments. Heap allocation is more expensive than stack allocation. Garbage collection Prolog systems typically employ garbage collection to reclaim memory that is no longer reachable, i.e., data structures that are no longer referenced by any active goals or variables. Garbage collection can be triggered automatically when memory usage reaches a certain threshold, or it can be invoked explicitly using a system predicate, example garbage_collect in SWI Prolog. Frequent garbage collection can indicate that your program is creating a lot of temporary data structures, which might be a sign of inefficiency. 3. Key factors affecting memory usage asterisk asterisk. Asterisk recursion depth asterisk deep recursion can lead to stack overflow errors if the stack size is limited. Each recursive call creates a new stack frame, consuming memory. Tail recursion optimization, TRO, can mitigate this issue in some cases. Asterisk choice points asterisk excessive choice points consume significant memory. Each choice point stores the current state of the program, including variable bindings and control information. Code that generates many unnecessary choice points can lead to memory exhaustion. Asterisk compound terms asterisk the creation and manipulation of large compound terms, lists, structures, consume memory on the heap. Consider using more efficient data structures or techniques to minimize the size of compound terms. Asterisk backtracking, while a core feature of Prolog, can impact memory usage. Each time a variable is bound within the scope of a choice point, that binding must be trailed. Excessive backtracking can lead to a large trail and increased memory overhead. Asterisk variable scope asterisk keep variables within the narrowest possible scope. This helps the garbage collector to identify and reclaim memory more efficiently. 4. Code examples and explanations asterisk asterisk. Example 1, deep recursion, potential stack overflow. Explanation asterisk. This naive implementation of factorial is not tail recursive. Each recursive call to factorial, N1, F1, pushes a new environment onto the stack, containing local variables N1 and F1, as well as control information. For large values of N, the stack can grow excessively, leading to a stack overflow error. Example 2, tail recursion optimization, TRO, avoiding stack overflow. Explanation asterisk. This implementation is tail recursive. The recursive call factorial_helper, N1, ACC1, F, is the last action performed in the clause. Prolog systems that support tail recursion optimization, TRO, recognize this pattern and reuse the existing stack frame for the recursive call, rather than creating a new one. This prevents the stack from growing excessively, allowing you to compute factorials of much larger numbers without stack overflow. Note, some Prolog implementations may require explicit configuration to enable TRO, example compiler flags. Example 3, generating choice points, memory consumption. Explanation asterisk. The first numbers version uses backtracking to construct the list. For each call to numbers, n rest, the system creates a choice point because the clause head might unify with the goal even after a solution has been found, although in this specific example, it won't. This is because, in general, backtracking is a fundamental part of Prolog's execution model. Even when a predicate only has one matching clause, the system might create a choice point if there's a possibility that the predicate could be resatisfied through backtracking. The second version, numbers_det, builds the list in reverse order using an accumulator, and then reverses the list at the end. This approach is deterministic, meaning that it generates only one solution without leaving any choice points. Deterministic code generally uses less memory than code that relies heavily on backtracking. Example 4, controlling backtracking, using cut. Explanation asterisk. The first _even predicate finds the first even number in a list. The cut operator is used to prevent backtracking after the first even number is found. Without the cut, the predicate would generate choice points for each even number in the list, even though we only want the first one. The cut commits the Prolog system to the first matching clause, preventing it from exploring other alternatives. Using the cut judiciously can reduce memory consumption by eliminating unnecessary choice points. Example 5, creating large compound terms. Explanation asterisk. This example creates a list of n atoms, A. Each call to create _list, n, a rest, allocates memory on the heap to create a new list cell, a rest. For large values of n, this can consume a significant amount of heap space. 5. Tools for memory profiling and debugging. Most Prolog systems provide tools to help you analyze memory usage and identify potential problems. Statistics predicates Prolog provides built-in predicates such as statistics, global_stack, used free, statistics, local_stack, used, free, statistics, trail, used free, and statistics, garbage_collection, count, time, to get information about memory usage, garbage collection activity, and other system statistics. These predicates allow you to monitor memory consumption during program execution. Profiling tools Some Prolog implementations, such as SWI Prolog, offer profiling tools that can help you identify which predicates are consuming the most memory or taking the most time to execute. Profiling allows you to focus your optimization efforts on the most critical parts of your code. 6. Practical tips for minimizing memory usage. Use tail recursion when possible, use tail recursion to avoid stack overflows. Ensure that your Prolog system has tail recursion optimization enabled. Avoid unnecessary choice points. Strive to write deterministic code whenever possible. Use cuts judiciously to eliminate unnecessary choice points, but be careful not to sacrifice correctness. Minimize heap allocation. Avoid creating large, temporary data structures on the heap. Use accumulators or other techniques to build data structures incrementally, rather than creating copies. Control variable scope. Keep variables within the narrowest possible scope. This helps the garbage collector to reclaim memory more efficiently. Use appropriate data structures. Choose the most efficient data structures for your problem. For example, if you need to represent a set of integers, consider using a sorted list or a balanced tree, depending on the expected operations and the size of the set. Groundness. Try to ground variables as early as possible. A ground variable, one with a specific value, takes up less memory than an unbound variable. Garbage collection. Understand how garbage collection works in your Prolog system. You can sometimes improve performance by explicitly invoking the garbage collector at strategic points in your code. However, excessive garbage collection can also indicate that your program is creating too much temporary data. Profiling. Use profiling tools to identify memory bottlenecks in your code. Focus your optimization efforts on the most critical parts of your program. Data representation. Consider representing data in a compact and efficient manner. For instance, if you have a large number of small integers, you might be able to pack them into a single word of memory. Incremental processing. If you are dealing with very large data sets, consider processing the data incrementally, rather than loading the entire dataset into memory at once. Avoid accumulating in the heap. Building lists or other data structures on the heap in an uncontrolled manner can quickly lead to memory exhaustion. For instance, repeatedly appending to a list using append/3 can be inefficient. Use techniques like difference lists, or build lists in reverse order with an accumulator, as shown in the numbers_det example. 7. Advanced techniques. Difference lists. Difference lists can be useful for efficiently building lists without excessive heap allocation. A difference list is represented as list, tail, where list is a list and tail is a pointer to the end of the list. This allows you to append to the list by simply unifying tail with the new element. *DCGs, definite clause grammars. DCGs are a powerful way to represent grammars in Prolog. They can be implemented efficiently using difference lists, which can reduce memory overhead. External data structures. For extremely large data sets that cannot fit into memory, consider using external data structures stored on disk. Prolog can interact with external databases or files to process data in chunks. Conclusion. Understanding memory management in Prolog is essential for writing efficient and scalable programs. By being mindful of the factors that affect memory usage, such as recursion depth, choice points, compound terms, and backtracking, you can write code that consumes less memory and performs better. Using the profiling tools and debugging techniques available in your Prolog system will help you identify and address memory bottlenecks in your code. Always prioritize writing clear, declarative, and well-structured code, and only resort to low-level optimizations when necessary. Remember that careful design and attention to detail are key to writing memory-efficient Prolog programs.